This is SpaceTime Series 29, Episode 33, for broadcast on the 18th of March 2026. Coming up on SpaceTime, what the birth of our Sun tells us about the evolution of our galaxy, making cosmic dust in the lab, and China looking at a landing site for its first manned mission to the Moon. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers studying the birth and early evolution of the Sun have uncovered how the shape of our galaxy has changed dramatically over the past few billion years. Our Milky Way galaxy is a barred spiral. It contains spectacular sweeping arms of stars and clouds of gas and dust, which is seen in traditional grand spiral galaxies. But there's also this thick bar of stars and gas across the galactic centre. The origins of these so-called stellar bars are still being debated. Stars are born in stellar nurseries deep inside molecular gas and dust clouds, often containing hundreds to thousands of protostars of varying masses and varying stages of evolution. It's thought a nearby exploding star called a supernova sent shockwaves out through the local cosmos as it exploded, causing one of these molecular gas and dust clouds to start to collapse under its own gravity, in the process triggering starbirth, including that of our own local star, the Sun. Eventually, gravitational perturbations, shock waves from other supernovae, jets of energy and mass shooting out from black holes, and/or powerful stellar winds from adjacent stars cause the stars in this nursery, including our Sun, to migrate out of their stellar nurseries and take up their positions in the galaxy, orbiting around the galactic centre, which contains a supermassive black hole known as Sagittarius A star. Our Sun and its solar system, including the Earth, orbits around this black hole some 27,000 light-years from the galactic centre. But astronomers believe it originally formed just 17,000 light-years from the centre. Now, a team of astronomers have uncovered evidence that the Sun migrated from its stellar nursery together with a multitude of siblings. The findings, reported in the journal Astronomy and Astrophysics, follow the creation of a massive catalogue of stars and their properties based on data from the European Space Agency's Gaia satellite. The discovery sheds light on the evolution of our galaxy, including the development of the rotating stellar bar-like structure at its centre. Scientists know our Sun was born around 4.6 billion years ago, more than 10,000 light-years closer to the galactic centre than where it is today. While studies of the composition of stars support this theory, this has long provided a conundrum for astronomers. See, observations reveal that the enormous bar-like structure in our galactic centre creates a sort of co-rotational barrier, which makes it difficult for stars to escape so far from the centre. And that begs the question, how do we get here? To answer this, Daisuke Taniguchi from Tokyo Metropolitan University and Takuji Tsushimoto from the National Astronomical Observatory of Japan carried out an unprecedentedly large study of stars which have similar temperatures, surface gravity and composition to that of our Sun. They used data from Gaia's treasure trove of observations covering some 2 billion stars and other objects both in our galaxy and beyond to create a catalogue of 6,594 so-called stellar twins, stars similar to our Sun. Now that's some 30 times bigger than any previous survey of its kind. From this, they were able to obtain the most accurate picture yet of the ages of these stars, carefully correcting for selection bias of stars which are easier to see. Looking at the distribution of ages, the authors noticed a broad peak of stars around 4 to 6 billion years old. That includes our Sun, and is evidence for similar stars, all of similar age, positioned around the same distance from the galactic centre. This means our Sun isn't in its current position by accident, but part of a much larger stellar migration. Now, the discovery sheds light not only on the nature of our solar system, but the evolution of the galaxy itself. The co-rotation barrier created by the stellar bar structure at the galactic centre wouldn't allow for such a mass event. However, the story changes if that stellar bar was still being formed at the time. The ages of our stellar twins reveal not only when the mass migration occurred, but also the time range over which the stellar bar itself was formed. The centre of the galaxy is a far less hospitable environment for the evolution of life compared to the outer regions. So it's rather fortuitous for us that our Sun and so many other stars did migrate outwards. The author's findings, therefore, illustrate a key factor in how our solar system, and in turn our planet, found itself in a region of the galaxy where life was able to develop and evolve. This is SpaceTime. Still to come, how to make cosmic dust in the laboratory, and China selects a landing site for what will be Beijing's first manned mission to the moon. All that and more still to come on SpaceTime. A new study examining how the building blocks of life are formed in extreme deep space environments has created cosmic dust in a laboratory. The findings, reported in the Astrophysical Journal, used a simple mix of gases, nitrogen, carbon dioxide and acetylene, to mimic the harsh and dynamic environments found around stars and supernova remnants. The study's lead author, Linda Lacerdo from the University of Sydney, says the results are shedding new light on how the chemical building blocks of life may have formed long before the Earth existed. By subjecting these gases to intense electrical energy, Lacerdo generated carbon-rich cosmic dust similar to the material found drifting between stars and embedded in comets, asteroids and meteors. The dust she created contains a complex cocktail of carbon, hydrogen, oxygen and nitrogen, collectively known as CHON molecules, which is central to many organic substances essential for life. Cosmic dust is known to form in extreme astrophysical environments, where molecules are constantly being bombarded by ions and electrons. Scientists can identify this dust in space because it emits a distinctive infrared signature, a molecular fingerprint that reveals its chemical structure. The dust produced in Lacerdo's experiments showed the same telltale infrared signatures, confirming the laboratory process closely mirrored what happens in space. Lacerdo says the research means scientists no longer have to wait for an asteroid or comet to come to Earth in order to understand their histories. Instead, you could build analog environments in the laboratory and reverse engineer their structure using their infrared fingerprints. This gives scientists an insight into how carbonaceous cosmic dust can form in the plasma puffed out by a dying red giant star or in cosmic nurseries where new stars are being born. One of the enduring questions in science is how life began on Earth. Scientists are still debating whether the earliest organic molecules formed locally on Earth, whether they arrived later on comets and meteors, whether they were delivered during the earliest stages of the solar system's formation, or whether it was some combination of all three. Between 3.5 and 4.56 billion years ago, planet Earth was bombarded by meteors, micrometeorites, and planetary dust particles originating from asteroids and comets. And these objects are thought to have delivered vast amounts of organic material to the Earth's surface. Yet the origins of that material remains mysterious. Lacerdo says covalently bonded carbon and hydrogen in comets and asteroid material are believed to have formed in the outer envelopes of stars, in high-energy events like supernovae and in interstellar environments. Now, she's trying to understand the specific chemical pathways and conditions which incorporate all of the CHON elements into the complex organic structures seen in cosmic dust and meteorites. Lacerdo and colleagues used a vacuum pump to evacuate air from glass tubes, recreating the near-empty conditions of space. Nitrogen, carbon dioxide and acetylene were then introduced. Now, the gas mixture was then exposed to around 10,000 volts of electrical potential for about an hour, thereby creating a type of plasma known as a glow discharge. Under this intense energy, molecules broke apart and then recombined into new, more complex structures. And these compounds eventually settled into a thin layer of dust on silicon chips placed inside the tubes. Lacerdo says the collected dust looks like glittering collections of cosmic material. The work will allow scientists to probe conditions that are otherwise impossible to study directly. By making cosmic dust in the lab, scientists can explore the intensity of ion impacts and temperatures involved when dust forms in space. And that's important for understanding the environments found inside cosmic dust clouds where life-relevant chemistry is thought to be happening. It also helps the authors interpret what a meteorite or asteroid fragment has been going through over time. That's because its chemical signature holds a record of its journey, and experiments like this help scientists learn how to read that record. Beyond insights into the origins of life, the authors hope to build a comprehensive database of infrared fingerprints from lab-made cosmic dust. Astronomers can then use this library to identify promising regions of space in stellar nurseries or in the remnants of dead stars and work backwards to understand the processes shaping them. Lacerda says that by recreating cosmic chemistry on Earth, the work opens a new window into deep stellar processes and the ancient steps that may have helped make life on Earth possible.
My supervisor, Professor David Mackenzie, he spent most of his career researching interesting forms of carbon. He actually discovered a type of carbon called tetrahedral amorphous carbon, which is quite a mouthful. Then I met him and started my PhD with him, and we started making these materials which were like amorphous carbons. When I say amorphous, I just mean no long-range order in the structure. And then we decided we'd include some oxygen and nitrogen in as well. The reason being, we started to see that more and more people were finding amorphous carbon, this particular type of carbon, in space, in the literature. And then we read more about it and we realized that really if you've got these gases that have carbon, nitrogen, oxygen, hydrogen in them that are around the envelopes of these giant dying stars, then there's no reason why you really shouldn't have oxygen and nitrogen reacting as well. And so that's when we decided we'd use this mixture and we'd make our own cosmic dust analog.
And you started with a fairly simple mixture of gases.
Yeah, it sounds quite simple in practice. So it's 3 gases. It's carbon dioxide, acetylene, and nitrogen. But what a lot of people may not realize is that when you're dealing with plasma reactions, and when I say plasma, I mean ionized gases, you're having lots of fragmentation of molecules and then lots of different reactions occurring. So plasmas themselves aren't very selective. What that means is that any types of products that you can make at an energy range, you probably will make. So the moment you add a third gas, for example, most experiments use 1 or 2 gases. The moment you add a third gas, you increase the complexity quite a bit. But what we were considering in our experiments is the fact that even if you have quite a complex gas mixture, so long as you know the parameters you began with, you're able to look at how a certain parameter, be it temperature, be it pressure, affects the product in its chemical fingerprint, in its infrared spectrum. If you know the conditions you start with in the lab and you know what the output looks like in the lab, then when you get a new sample from space, just by looking at the trends, okay, with temperature, I get an increase in this certain species, in this certain peak, this type of bond, then you can kind of back calculate and say, well, if I have a dust particle that has this chemical signature, it must have experienced these formative conditions in its lifetime.
You created CHON molecules. What are they?
CHON is carbon, hydrogen, oxygen, nitrogen. We use the term quite loosely. They're not quite molecules. They're actually a network structure. So it's an amorphous carbon backbone. Again, amorphous just means no long-range order in the structure. And it's got oxygen and nitrogen and hydrogen attached. So it's a very chaotic mixture. It does quite closely resemble the insoluble organic matter found in meteorites. And that is largely why we're interested in it as well, because trying to find natural processes that make these mixtures that are found in meteorites is quite difficult. And it's nice to have a way to replicate an indicative process of how the subcomponents of meteorites may form.
Over the last few decades, there have been more and more examples found of amino acids floating out there in space. We think they're quite common now. Is that something you'd like to recreate, or is that something you have recreated, or are you willing to sort of just let Miller-Urey experiment cover all that?
Yeah, so the Miller and Urey experiments and also some experiments by Carl Sagan have really inspired me growing up, but now inspiring my work as well. I will stress that our experiments, they are a little bit different to what Miller and Urey did, and they are a bit different to amino acid experiments. When we're looking at building blocks of life and how organic material got to Earth, yes, it's true that a lot of it may have been these well-preserved amino acids from space, but we actually know from specific type of meteorite that falls called a carbonaceous chondrite that most of the organic matter in meteorite is in this insoluble organic form. And so trying to recreate that insoluble form is really what we're after here.
Carbonaceous chondrites, they're some of the oldest substances we've ever found. What's it like to handle something like that?
Yeah, it's It's been quite spectacular, in particular talking to meteorologists. I went to the meteorological conference this year, which was actually held in Perth, and I learned so much from people who were studying the real thing that it did really, it inspired me for my work trying to make analogues. And I think something that I always think about is that natural processes, things that, occur in these really extreme conditions in space, they've been happening for millions of years, and they are so very complex, and they are so remarkable in many circumstances. The fact that you have this range of environments that occur in space. And so I often feel like, no matter how many different dust samples I make, maybe one might be a little bit similar to something, but I can never reach that full complexity. And I think that challenge and that knowing that the universe is so grand and it's so good at making these dusts is a nice little thing to think about. The fact that the more we know about the universe, there's even more we don't know, and we won't be able to replicate, or maybe it'll take a lot longer to replicate. There'll always be something to know.
I completely geeked out when I got to have a close look at a Murchison meteorite fragment, so I can understand what Perth would have been like for you. Do you think we'll ever reach a stage where what we now see as a chemical interaction, we witness it becoming a biological interaction?
I'll answer that question as best I can. I think it's important to consider where, expertise lies. I'm someone with a physics and a chemistry background, and I can do the reactions that I know about, and I can understand that science. But I think in order to get from something that is abiotic, not lifelike at all, to something that is biotic, will require a huge team of scientists coming from all sorts of different backgrounds. When you start looking into how amino acids then form larger structures like DNA and protein, you realize the degree of biological complexity that is required. And there are still so many unknowns with that. I think what is nice about science and about this type of interdisciplinary science is that every research group working on these types of problems makes a small step. And then when you look back at it, we've actually learned quite a lot in the last 10, 20, 30 years that we didn't know before. And it's really that cumulative knowledge, I think, that will lead to breakthroughs. Standing on the shoulders of giants. Yeah, absolutely. I love every time I open Google Scholar, where we get our literature from that we read before we write papers, seeing that quote, standing on the shoulders of giants. I do think about that a lot. Other people have studied dust. Other people have made different types of analogues of dust. And I think it's so important that myself as a researcher and my supervisor, we have so much respect for the scientists who have gone before us. And we hope that maybe the dust we've made inspires someone to try out their own experiment in a different way. I think that's what science is all about. It's not about holding it for yourself. It's about trying to encourage everyone to have a look and have a go. One of the big problems we have when we go to Mars or go to Europa or go to Enceladus, any of these places, even Titan, I guess, any of these places where we think life may have been in a situation where the environment was habitable enough for it to exist, we always wonder, is that really, can we tell what life is? We went to Mars, we did the soup experiment, and people are still scratching their heads over it. Yeah, I think that there's a really beautiful thing about how complex life is. People's definitions of it are also very different, and that's something to be very mindful of. What life means to one person may not be what it means to someone else. A lot of people will define it at an amino acid level, but a lot of people say, well, no, you need to wait until you have larger structures like RNA and DNA and protein before you really call that life. And I think that there's a whole philosophy aspect of this as well, and a religious aspect that scientists, we can try our best to answer, but at this stage there are so many unknowns, and it's really important to be respectful of how many different opinions there are for these types of topics. That's Linda Lacerda from the University of Sydney, and this is SpaceTime. Still to come, China selects a landing site for its first manned mission to the moon. And later in the science report, a new study has shown that taking a daily multivitamin could help you slow biological aging. All that and more still to come on SpaceTime. Beijing's identified 4 possible landing sites for what will be China's first manned mission to the lunar surface. Scientists used orbital images to study the moon's equatorial rim bode region.
A report in the journal Nature Astronomy says a manned mission to the lunar surface was a high priority for Beijing and likely to happen around 2030. The areas being looked at are scientifically valuable because they include varied terrains and materials which span long periods of lunar history. And that's important for understanding how the surface and interior of the moon have changed over time. Of special interest is a dark layer of volcanic debris, a basalt plain called Sinus Aestum, two separate valleys formed by volcanic and tectonic activities, and the surrounding highlands. This is SpaceTime. And time now to take another brief look at some of the other stories making news in science this week with the Science Report. A new study has shown that flu jabs in the United States this season have been shown to be less effective against a fast-moving strain now spreading in Australia. A report in the Journal of the American Medical Association warns that influenza A H3N2 subclade K J241, known as Super K, is spreading faster and earlier in Australia than during typical flu seasons. It was also dominant across the United States during its winter months. Scientists assessed the antibody responses of 46 people who received flu jabs in late 2025 against a series of strains, including Super K. They say the samples showed a weaker antibody response to Super K compared to the other strains. It also appears that Super K can partially invade immunity from prior infection with similar flu strains. The authors say there is still a modest response to Super K, so while flu shots are less effective than normal, they're still likely to offer at least some protection. A new study has shown that taking a multivitamin pill every day could help slow biological aging. The findings, reported in the journal Nature, are based on a study of around 1,000 adults aged around 70. The authors found that in older adults, two measures of biological aging were slowed in a small but meaningful way after 2 years of daily multivitamin use, with greater benefits for those who began the trial with already accelerated biological aging. A major new study has shown that social media and video games are linked to poorer developmental outcomes in kids and teens. The findings, reported in the Journal of the American Medical Association, showed digital media use had modest but consistent links with poorer mental and physical health outcomes. To reach their conclusions, the authors pulled data from 153 previous studies. They found that social media was linked to a range of worse outcomes, including depression, problematic internet use, substance abuse, and lower academic achievement. Video gaming was found to be linked with higher aggression and also problems with general behaviour. Norton are now offering their Scam Genie AI as a free app in ChatGPT. With the details, we're joined by technology editor Alex Zaharov-Reutt from Tech Advice Start Life.
Norton announced something called Norton Genie. This would have been sometime last year. It's an AI scam detector that at first you could download on iPhones, and then it became available for Android. And it helped end users to determine whether, from a screenshot of an SMS message or some sort of message in social media or elsewhere, like an email, as to whether or not what you were looking at was a scam or not, whether the AI engine inside this app could detect that something was malicious. And we all know that the bad guys are using AI to fake websites, to eliminate the telltale spelling errors, to completely clone a site and make you think that when you're logging in and giving them a username and password, and maybe even the two-factor authentication code that somebody else will immediately type in to hack into you for real, is legit and looks so real. So people have been turning to AI, not just with the Norton Genie tool, but into ChatGPT and Gemini and others to ask the AI whether something is a scam. And this is because people have been asking Google for years about medical conditions, and they now ask AI. They treat AI like a doctor, a financial advisor, a nutritionist, a therapist, psychologist, and we often see where it says, "I am not a doctor, please seek proper medical advice, but here's my answer." So the interesting thing here is that ChatGPT can be used for free, and so can the Norton app. And often when you have these more advanced facilities, you've got to pay $20 US a month for ChatGPT or $33. But here you can download the Norton Genie app into ChatGPT, even the free version, and then you can ask it at you put the @ symbol, you put Norton. This email says my account will be locked if I don't act now. Is this a scam? Or @Norton, I got a text about a missed delivery with a link. Should I click it? Or @Norton, this message looks like it's from my bank, but something feels off. Is this the real online deal, or are they trying to steal my information? And there are tools that only check whether a link is known to be malicious. But the Norton Genie app is looking at the full context of a message, and it's examining the language, the intent, and the tactics that are being used alongside URL and domain checks to spot common scam patterns like impersonation, which they're always trying to do, the pressure to act quickly, which is scammers' tool in trade. They want you to urgent, you've got to act now. And then you're told to go and buy an Xbox game card to pay off a tax debt or something. It's ridiculous. But people fall for it. Or requests for sensitive information. So you just log into ChatGPT, you open the apps section, you find and enable Norton. And then when you want to ask Norton something, you go @Norton and then ask the question. So it's nice to see the good guys are using AI to help us fight against the bad guys using AI.
That's Alex Zaharov-Reutt from techadvice.life. And this is Space Time. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from SpaceTimeWithStuartGarry.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to SpaceTimeWithStuartGarry.com for full details.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.